Recall that a polynomial is a sum of terms. If it's written in descending order, it's going to be like this. So you'd have your biggest exponent first, x to the n. That would be accompanied with its coefficient, which we'll call a sub n. So this is the coefficient of the nth term. Here's the coefficient of the next term down, n minus 1 times x raised to the n minus 1. So it goes down. So this could be an x to the fifth, x to the fourth, x cubed, on down to x to the first, and the constant. The term with the largest exponent is called the leading term. Sometimes it's called the dominant term. It determines the majority of the characteristics of the whole polynomial. And another important thing to know is that any polynomial of degree n, where n is the biggest exponent, has n complex zeros, as long as we take multiplicity into account. Remember that all real numbers are also complex numbers. So let's look at this one. Not all cubes will factor by grouping, but this one looks pretty hopeful. If we look at the first two terms, we could factor an x squared out of this, which should leave us x minus 2. Then you want to bring down whatever this sign is. I have a tendency to just cheat and carry this over and then see if I can make it work. So minus what times x would be minus 4x? This would have to be a 4, right? So minus 4x would be minus 4x. Minus 4 times a negative 2 would be a plus 8. So this checks out. The common factor between these two is now the x minus 2. So if I factor out the x minus 2, if that's gone, that's going to leave me an x squared from the first one, minus 4. Well, x squared minus 4 is a difference of squares. This has been factoring by grouping. That's what this is called. And you need to know how to do this. You can't replace this with the quadratic formula. This one is a difference of squares. The x squared minus 4. Anytime you have a square minus a square, that will factor as the square root of the first one, and then a plus and a minus, and the square root of the second one. Bring down this other one. So notice that I've actually got two factors here that are the same. I could write this as x minus 4 squared times x plus 2. The zeros are what we get when we set this equal to 0. To make this equal to 0, I can set each factor equal to 0. This one's going to give me a 2. This one will give me a negative 2. This one is just a single factor, so this one has multiplicity 1. This one is squared, so this is actually 2 of the factors. So it would have multiplicity 2. And notice that we've got 1, 2, 3 matches up with the x cubed. Let's look at another one. Here, notice that I've got an x in every term. As a matter of fact, I have at least an x cubed in every term. So that's a common factor. And every one of the coefficients will divide by 5. So I could make life a lot easier if I just factored out this 5x cubed first. Let's see, that's going to leave an x squared minus 10x plus 29. Now, if I set this factor, if I'm looking for zeros, I set the whole thing equal to 0. So 5x cubed is equal to 0. I can divide by 5. That gives me x cubed is equal to 0. Of course, the only thing you can cube and get 0 is 0. So x equals 0. 0 is a 0 of multiplicity 3. Now I had an x to the 5th, so I've got 2 more I got to find. This is not going to factor. We're not guaranteed that everything factors. So let's see what would happen. Even if it would factor, I could still use the quadratic formula. So I've got negative 10, negative b, plus or minus the square root of b squared, negative 10 squared, minus 4 times a times c, all over 2 times a. So we got 10 plus or minus the square root of 100 minus 4 times 29, 36, carry the 3, 116. Oh, it not only doesn't factor, it doesn't even have real numbers. This is going to be 10 plus or minus the square root of a negative 16. So 10 plus or minus, this is going to be 4i over 2. I can write this as complex numbers by saying 10 over 2 plus or minus 4 over 2i, which will be 5 plus or minus 2i. Now this is 2 separate factors. So my zeros, I've got x equals 0 of multiplicity 3, x equals 5 plus 2i, and x equals 5 minus 2i, each have multiplicity 1. So that's 1, 2, 3, 4, 5, x to the 5th, that's all of them. Now these wouldn't be graphed, so the graph of this is only going to go through the point 0, 0 as far as x-intercepts. But if we're looking for zeros, then these still count. They're not x-intercepts, but they are zeros. What about here? This is a quadratic wannabe. Anytime you've got a constant, and then you've got an exponent in your middle term, and then your exponent in your dominant term is exactly double the exponent in the middle term, then this has a quadratic form without actually being a true quadratic. Let's see if there's any chance this could factor. If I'm going to factor something like this, I've got a tendency to just take whatever the variable is in the middle, and that's the version I put here and here. So an x squared and an x squared. There's no number in front of the x to the 4th, so this times this would give me the x to the 4th. This times this is going to be an x squared term, and this times this is going to be an x squared term, and they have to add up to a 1x squared. These numbers have to multiply out to a 6. So this factors the same exact way it would if it was x squared plus x minus 6. The only difference is in the exponents, and putting these squares here is going to take care of that. So the factors of 6, 1, 6, 2, and 3, that subtract to give me 1 would be the 2 and the 3. To get a positive 1 out of that, it would have to be a positive 3 and a negative 2. So if you double check, you'll see that this is the factorization of that. Now I can set my factors equal to 0. It's a square, don't lose that. And even though these are quadratics, I don't have to use the quadratic formula because there's no middle term. I can just say this is x squared equals 2. So x is going to be plus or minus the square root of 2. That's a square. This is going to be x squared equals negative 3. So x will be plus or minus the square root of negative 3, which will be plus or minus the square root of 3 times I. So I have two real zeros, the square root of 2 and the negative square root of 2. And two imaginary zeros, square root of 3i and the negative of the square root of 3i. Notice the I is not in the radical. This is my 4 zeros. This was an x to the 4th, so it's good to go. So that's an example of how you can always find your zeros if you've got a polynomial that will factor.